So the topic is that is called radioactivity. So first we actually go through some formula and then we will start some problems. So the thing is that this is nothing but, you can say, radioactivity. So the thing is radioactivity, and it is one of the common topic. So the thing is that, so what we know that radioactivity that can be measured, like that we already know that you can say when there is a possibility that we have discussed that inside a nucleus electrostatic attractions that is counterbalanced by the short range nuclear force, and the nucleus becomes stable. So that despite of the forces being balanced, we know that many nuclears are unstable because of the nuclear size, or you can say the limited range of nuclear force. And due to slight imbalance in small size nucleus, what we do that the nucleus spontaneously that will disintegrate into other nucleus, and this phenomenon of continuous disintegrations that is called radioactivity. And we know that there are three kind of rays that are produced naturally occurring radioactivity, that is, you know, that alpha rays and beta rays, and you know that gamma rays. And the thing is that when you can say a nucleus disintegrate and produce alpha ray, it is said to be alpha ray, and experimental evidence shows that, you can say, you know that an alpha ray that is consist of positively charged particle, and each one being the helium nucleus. That means we know that this is 92U 238, and that will be, you can say, break into daughter nucleus, and that is the helium, and that is nothing but, you can say, uh, alpha particle. So that is, you can say, about the alpha decay. And you know, in case of alpha decay, if this is the parent nucleus, and if alpha particle will be emerged, this is the daughter nucleus, then this will be decreased by 4 a, and z will be decreased by 2, and as well as you can just know that is nothing but helium particles. So that's why the total is being constant. So you know that is the case of alpha particle, and so that means in several problems they will, you have to find the number of alpha particles. Now consider the beta rays, and of course we know that beta rays that is deflected by the magnetic field in a directions to the oppositely positively charged alpha ray, and that is known as a beta ray. And we know that there should be a positive beta minus and beta plus. If we consider beta minus decay, then we know that if this is the parent, then that will be the daughter, because this is a negative decay. That means electron emitted in beta minus decay does not actually exist within the parent nucleus and is not one of the orbital electrons. Instead, what we can say that the electron is created when a neutron decays into a proton and electron.
না, আপনার প্রেজেন্টেশনটা দেখা যাচ্ছে না।
Oh, it is not visible. Okay, just a minute. So, is it visible?
না স্যার, এখনো দেখা যাচ্ছে না।
Okay, it is not visible. So, Just a minute then. So this is the concept of beta minus decay. What I am saying that the electron that is emitted in beta minus decay, that does not actually exist within the parent nucleus and is not one of the orbited electrons. But we say that instead the electron is created when a neutron decays into a proton and electron, and when it occurs, the proton number of the parent nucleus, that is, increases from Z to Z plus 1, and the nucleon number remains unchanged, and that is beta plus decay. And that is a second kind of beta decay that will sometimes occur. So in this process, you can say, in this process, what we can say that the particle emitted by the nucleus, you can say the particle that is emitted by the nucleus is a positron, is a positron rather than, you can say, electron. So a positron are also called, you can say, a beta plus. So a positron that will also called a beta plus particle has the same mass as the electron but carries a positive instead of, you can say, negative. So in that particular case, what we can say that this is the daughter nucleus, and you can say that is, so that is nothing but the positive decay. Now the case is, there is also another term that is called neutrino, that is also, you can say, and that is one of the thing that is still now discovered, different types of neutrino. And the thing is that, so this is nothing but a neutrino. That means when a beta particle is emitted by the, you can say, radioactive nucleus, we know that energy is simultaneously released, and experimentally, however, it is found that most beta particles do not have enough kinetic energy to account for all energy release. That means if a beta particle carries away only a part of energy, where does the remainder go? So in 1930, Pauli proposed that a third particle must be present to carry away the missing energy and to conserve momentum. That Fermi later developed a complete theory of beta decay and named this particle as neutrino, little neutral one, that is neutrino. And because it had to be electrically neutral and have little or no mass, you can say, although it eluded detections for many years. So neutrino was finally detected experimentally in 1956. In, for instance, of the beta decay, they will say that there is some imbalance in the energy, and from that actually they decide that other than the beta particle there is some quantity which is called neutrino. The bar above the this mu is included because neutrino emitted in this particular decay process in an antimatter neutrino or antineutrino. So a normal neutrino is without bar, that is emitted when beta plus decay occurs. And of course, you can say the neutrino has some properties that you should remember. The first property, it is, you can say, zero electric charge, that is the first property. The second property is a mass much smaller than that of electron. So we can say a mass that is much, you can say, smaller than that of the electron, but you can say probably not 0. And recent experiments suggest that the neutrino definitely have mass, but the value is uncertain, and perhaps it has different. And the third point, that a spin of half is present. And you can say the fourth point, that is, you can say very weak interaction, very weak interaction with matter, very weak interaction with matter, making it making it quite difficult, quite difficult to, you can say, detect, quite very difficult to detect. So that is the concept of, you can say, neutrino. And the last one, you know about the gamma decay, that you know that very often a nucleus that undergoes radioactive decay is left in an excited energy state. So you can say the energy that is released, it may be in the form of gamma decay, and that may, a nucleus may reach an excited state, you know, as a result of maybe collisions with some other particle. And it is very common for a nucleus to be excited state as a result of alpha or beta decay. And you can say the following sequence of events represent, you can say, typical situations in the gamma ray occur. That means first, you can say, uh, like this is a boron 5, and this is a, you can say, excited, you can say, carbon, that is antineutrino. And then this excited carbon will be decays and release gamma. So the thing is that this asterisk means that the carbon nucleus is left in an excited state by the following decay, and after that it will be released like that. So uh, if the questions comes like that, say the questions is, what is the, you can say, wavelength, what is the wavelength of the 0.186 MeV gamma ray photon emitted by radium, emitted by, you can say, radium 22688. So what should be the answer? That means the question is, you can say that what is the wavelength of 0.186 MeV gamma ray photon emitted by radium. So we know that the photon energy is the difference between two nuclear energy level, that we know. And you can show that what we know, that the photon energy is nothing but is the difference between two nuclear energy levels, two nuclear energy levels. And we know that equation, initial energy minus final energy equals to h mu. Here we are using mu to denote neutrino, so we just write hf, that is the relations, and f is the frequency. So what we can know, that this is the energy difference, that is nothing but hf, and of course f into lambda is equals to c. So you can say lambda can be written as hc by, this is a change of energy, because we have to find the wavelength. So first we can convert the photon energy into joule. That means the energy that is given is nothing but 0.186 into 10 to the 6 eV. And the thing is, This is 1.6 into 10 to the minus 19 by 1 eV, and you will find it in joule. And if you just place the value, you will get the value of lambda, that is Hc by del E, and you will get something else. So that is the one of the simple thing that can ask. And you know that there is also the concept of stability of a you can say uh, nucleus. That means there is a neutron proton ratio, and you know that stable nucleus have the n by p either equal to 1 or more than 1, and the ratio is nearly 1 for light nuclei up to calcium, and then it increases up to 1.6 for heavy nuclei. So the thing is that we know. Now if we go to the thing that is called radioactive decay. So the thing is that the question of which radioactive nucleus in a group of nuclei that will disintegrate at a given instant. That means if we can say there are n number of parent nucleus that will decreases. So after time t, what should be the relations between n initial and the after time t, what should be the value of the you can say number of atoms that is remaining. So the thing is that from that we are measure the radioactivity. So the radioactivity of an element first is measured in terms of activity. That means the first thing that radioactivity, that is you can say of an element, that is you can say is measured, you know that in terms of activity. And I am not going details, that we know that if n be the number of nuclei, if you can say this capital N be the number of nuclei that is present in a radioactive sample, at an instant, then we know then activity of this sample you can say is given by AC is equals to minus dN with respect to dt, that we can say. And what should be the fundamental law of radioactivity, that we know that if we consider that at t equals to 0, we say that there are n not parent atoms you can say in a substance, and after t you know that n atoms are left undecayed, then uh, that means from t equals to so from t equals to 0 to t equals to t, that n0 minus n atoms are decayed to their daughter element. So we know activity is nothing but if we take the magnitude of the activity, that is nothing but dN with respect to dt. And according to the radioactive law, according to the you can say according to radioactive law, what we find that dN with respect to dt, that will varies with n, or you can say this activity, that is dN with respect to dt, that can be written as lambda n, where lambda is a proportionality constant, and that is called you can say decay constant for decay process. And of course the value of decay constant that will vary you can say differs from different element, and you know that lambda value is high, the element will have high value of activity, and if lambda is less, then we can say the activity will be relatively less. So from that we will get that. So the decay constant, you can say, of a process can be given as activity per atom, activity per atom. And from the equation what we will get, that dn with respect to dt, that is equals to minus lambda n. That negative sign shows that dn with respect to dt, that means the rate at which the activity element are disintegrating is negative, or number of, you can say, active element are decreasing with time. Number of active element is decreasing with time, so we are taking negative. And we will say if we that integrate it, then you know the integration, we will find n equals to n0 e to the power minus lambda t. We will get this particular equation. So that will give you the number of active parent atoms present at time. That means that will give you, you can say, that number of, you can say, active uh, parent atoms, number of active parent atoms in, that is present at time t in the mixture, that we know that n equals to n0 e to the power minus lambda t. And uh, if we just put lambda is multiplied both sides, then it is lambda n naught e to the power minus lambda t, and lambda is nothing but activity, and this is activity at initially. So that is, you can say, that is lambda n0, that is nothing but initial, you can say, initial activity. So that means if you draw the graph like that with t respect to n, it is like that exponentially decreases like that, and that is, you can say, n naught. So this is the one of the formula that we will get. And of course you can say the number of nuclei decayed, that is, you can say, if we find that you can say number of nuclei that is decayed, and that is, you know, that it is n naught minus n. So we will get n naught minus n naught e to the power minus lambda t, and if we take n naught common, e to the power minus, that is the, you can say, number of nuclei decay. So, and there is also one concept, that is, you know, that half life time, that is half life time, and it is nothing but what we know, that you can say at t equals to 0, in, you can say, at t equals to 0, in not nuclei are present. So we have to find that at time equals to t, when n naught by 2 elements are present, you have to find this value of capital T. So if we find that, we know the formula is n equals to n0 minus lambda t, and we know that at t equals to t, we can put n equals to n naught by 2, and if we put this, then what we find, that this is ln2 by lambda, and that is nothing but 0.693 by lambda. That is nothing but half life and the relations between, you can say, half life and the relations between decay constants. Now the thing is, number of nuclei present. If we say that number of nuclei that is present after n half life, after n half life, that is after a, you can say, time t equals to n t half, then what we will get, n equals to n naught e to the power minus lambda t. So you can say n naught e to the power minus lambda, this is, you can say, lambda n t half. That means we are finding that after a time when t equals to n t half, what should be the value of this, and that is n naught e to the power minus lambda n ln 2 by lambda, and this is n naught e, you can say ln 2 to the power minus n, we can write like that ln by, so we can write like that. So you can find n naught 2 to the power minus n, that means n naught half to the power n, that means n naught by, you can say 2 to the power n. What does it mean? That means, so if n naught is initial number of atom, so after first half life what will be the, that is n naught by 2. After second half life, that is n naught, like that. After third half life, this is this, and it is goes on like that. So after n half life, what we find, that is half to the power n, that is nothing but this one, we will get that. So that is one type of the thing that we should know. And another important thing that is important, that is you can say alternative, uh, this is form of decay equation, alternative form of decay equation in terms of half lifetime. That is one of the important form that would be useful when we are solving different types of problem. The thing is, say we can say that let a radioactive element, that is X, that decays to a daughter nucleus, you can say Y, with a decay process, and we know that X can be written as it being Y. Initially, we know that initially this N0 nuclei of element X are present, and then then after time t, number of nuclei that is present in the sample is, we know, given by decay equation, that is n equals to n0 e to the power minus lambda t, that we know. If we rearrange the equations, then you can write like that ln n by L naught equals to minus, you can say lambda t, if we can rearrange the equations like that. And t is, you know, ln t by lambda, so lambda is nothing but ln 2 by t. So from that, what we can, this is t, so what we can get, that ln n by n naught, that is minus, in place of lambda we can place this into t, or ln n by n naught is ln 2 minus t by t. And the thing is that if we take an antilog on both sides, then n by n naught, you can say, equals to 2 to the power minus t by t, or you can say it can be represent 2 minus t by t. This is the another form that we can write. This equation is an, you can say, alternative form of decay equation that is used for numerical application, that would be useful for numerical application. So what are the corresponding formula that we will get? If we summarize only the formulas, then what we can say, that we know that activity can be written as dn with respect to dt, That is the first one. The second one you can write like that. If we take the magnitude, then we will find a formula, that is n equals to n0 e to the power minus lambda t, and as well as there is another form that we also find, that is n equals to n0 2 to the power minus t by t, and that is 4 is, you can say, we are finding that the activity is also written like that. The formula 5, you can say that number of nuclei that is decayed is n0 1 minus e to the power minus lambda t, and 6, you can say, that is half life can be written like that, ln2 by lambda, and the 7, that you can write that n equals to n naught by 2 to the power n. So that is the corresponding formula, and all the problems in radioactivity that will use one of the formula. So if we do one of the problem, then say just the problem number 1, that is the, and there is also another thing that you should know, that is the you can say simultaneous decay mode, or you can say that accumulation of radioactive element in radioactive series, that you should know. Then we will go to the problem. That means this is one thing that you know, that accumulation of a, you can say, radioactive element in, you can say, radioactive series. Accumulation of a radioactive element in radioactive series. That means, say, we know that in radioactive series, we know that each element decays into its daughter nucleus until a stable element appears. So if we consider a radioactive series, that after this disintegration we get A2, and that is a different disintegration, we get A3, and this is lambda 3, we will get like that. So if we analyze mathematically the above series, we assume that initially at t equals to 0, in not atom of parent nucleus A1 are present, which decay to the element A2 with a decay constant lambda 1. So after time t, the number of undecayed nucleus of A1 present. So if we say that after time t, the number of undecayed nuclei of A1 that is present at a time instant, t, that can be written like that, n1 equals to n0 e to the power minus lambda 1 t, n1 is equals to n0 e to the power minus lambda 1 t. So due to disintegration of A1, the nuclei of A2 are formed, and this start decaying with a decay constant lambda 2 to another element, that is, you can say, A3. So at an instant t, n2 undecayed nuclei of A2 be present. That means you just see the figure, A1 from A1 এ যেটা পড়ে থাকলো সেখান থেকে আবার A2 এলো, A2 আবার decay করছে. So what I am saying, that let and at an, you can say, instant t, that into, you can say, undecayed nuclei of A2 be present, so what we can say, then the decay rate of A2 at this instant, you can say, can be given as, we know the decay rate of A2, that is lambda 2 into N2. So due to this integration, what we know, that A1 and A2 is produced, and the production rate of nuclei A2 will be decay rate of nuclei A1, because we know that the production rate of A2 at an instant can be given. So if we find that production rate of A2 is nothing but lambda 1 N1, and now in further time dt, if dn2 nuclei of element A2 are accumulated, then we have to find the accumulation rate. That means now in a further time dt, if this dn2 nuclei of element A2 are accumulated, then disintegrate rate that can be given by lambda 1 n1 minus lambda 2 n2. And if you solve these equations, you will find the value of n2, that is one of the formula, that is lambda 1 n naught by lambda 1 minus lambda 2 e to the power minus lambda 2 t e to the power minus lambda 1 t. That is also, you can say, one of the formula. So we see that in the beginning N2 is 0, and due to disintegration of A1 and A2 that is being formed, and you know that the amount of A1 is decreased and that amount of A2 is increased. So the decay rate of A2 increases and that of A1 is decreases. So after a time, you say that when both decay rate become equal, the element A2 will be said to have radioactive equilibrium. That is called radioactive equilibrium, when the you can say yield of the radionuclide A2 is maximum. So that is one type of thing that you should know. And if we find that let's solve one problem, then it is understandable. The problem is, say that nuclei of radioactive element A, radioactive element A are being produced at a constant rate alpha. The element, say, has a decay constant lambda. So at time t is equals to 0, there are a naught nuclei of the element that means nuclei of radioactive element A that are being produced at a rate constant rate alpha. When element has a decay constant lambda, at time 0 there are n naught nuclei of the element. So first question is, you have to calculate the number n of the nuclei of A at time t. You have to calculate, you can say, the number n of the nuclei at A, nuclei of A at time t. So in that particular questions, the nuclei of radioactive element A are being produced at a constant rate alpha, and you can say the element has a decay constant lambda. At time t equals to 0, there are n naught nuclei of the element. So you have to calculate the number n of the nuclei of A at time t. So here the rate of formation of the radioactive nuclei, you can say that if we consider this particular case, there is some differences there. The difference is the radioactive element A that you can say are produced at a constant rate alpha, that is given. So you can say that here the new thing is that the rate of formation, the you can say the rate of formation of radioactive nuclei of radioactive nuclei is alpha. So the rate of decay, you know, the rate of decay of radioactive nuclei is lambda n. So what we can say, dn with respect to dt, that is not, that should be alpha minus lambda n, because alpha is the rate that being produced at a constant rate, that means the element is being produced, and that is the decay. So what we can get, alpha minus lambda n. Now if you can solve it, dn by alpha minus lambda n, that is equals to dt, and if we integrate both sides, then that should be log e alpha minus lambda n by minus lambda, and that is t plus some constant, and it is given that at t equals to when 0, that value of n equals to n naught. If value is n equals to n, if we put that, then the value of a that will come out log e alpha minus lambda n naught by minus lambda, that is the value of a. And now if we put this value of a into that particular equations, you will find that that should be you can say log alpha minus lambda n by minus lambda plus t, you can say equals to t plus log e alpha minus lambda n by minus lambda, or you can say log e alpha minus lambda n by alpha minus lambda m naught, that is equals to minus lambda t. And if you can solve it, what we will get, that alpha minus lambda n by alpha minus lambda m naught is equal to minus lambda t, and we will get n equals to alpha by lambda 1 minus e to the power minus plus n naught e to the power minus lambda t. So that is the value of n. So এটা বোঝা গেছে রাজিয়া? না বোঝা গেল না? So if I give some problems, that is not the problem, you can say that is one of the problem. So the thing is that let solve some problem. You can say okay, I am giving some problem, you just solve it.